Okay, so I'm going to talk about experiment 5 where we're thinking about concentrations of acid and base solutions. And I'm going to go through the individual parts of this experiment, how we're reading and all the measuring tools, and how we do the calculations. So we start this experiment by preparing a stock solution of our oxalic acid dihydrate. So the H2C2O4 is oxalic acid, and these two water molecules indicate that it is the dihydrate form. So that's going to be important for the molar mass of this compound. We're going to start off by weighing out the solid into a weighing vial. It's possible that this will be done for you just to avoid any issues of having too many people at the balances at a time. So once you have the solid, you're going to add the solid to your volumetric flask. Using a funnel. Then you're going to rinse the vial with distilled water that is provided in marked bottles for you. And you're going to do this several times and add the rinses to your volumetric flask. Then you're going to fill the volumetric flask halfway with water. It's important to fill it halfway first because it's very hard to dissolve your solid when it's all the way full. So you're going to swirl to dissolve the solid. And once the solid's been dissolved, you can fill the flask to just below the marking with your distilled water. To get to the line or the marking on the flask, you're going to use a dropper to get the meniscus of your solution to the line or the marking. Sorry, that should say marking on your flask. If you're having trouble identifying which is the correct marking, be sure to ask your instructor. Then you stopper your solution, hold the stopper to make sure it doesn't fall down or fall out, and then you invert several times to mix, anywhere between 3 and 10 times. The more you invert it, the better your solution will be mixed, and the more uniform your solution will be. Once you've prepared this solution, and if you want to see what that kind of looks like, we have a video provided in Canvas for you. You'll need to calculate the molarity of the solution or the concentration of this solution. Because we use a good amount of the solid, we'll be able to calculate the concentration with a lot of sig figs. So we'll have 4 sig figs for this concentration. The more you have, the more precise your calculation of your unknown concentration will be. If we're starting with 1.425 grams of our oxalic acid dihydrate, we need to first figure out how many moles of the dihydrate we have. The way we do this is by using the molar mass. And again, it's very important to include the mass of the 2 water molecules because those are included in the molar mass of the solution. And then we know that there is 1 mole of the oxalic acid for every mole of the oxalic acid dihydrate. So that's how we convert from 1 mole to the other. This gives us 0.0113 moles of the oxalic acid. And to get the molarity, we're going to divide by the volume we use, so 100 milliliters. And we know that there's 1,000 milliliters in a liter, so we're able to convert to liters that way. and we get 0.1130 molar of our oxalic acid solution. And this is the solution that you'll be using to titrate your unknown sodium hydroxide solution. Well, let's talk about how we do the titration itself. When you're doing the titration, what you're going to be doing is thinking about the concentration of the unknown sodium hydroxide solution. So we're going to be adding water and indicator to an Erlenmeyer flask. The purpose of the indicator is to change color when you've reached the end point of your titration. After you've added the water and your indicator to the flask, you're also going to add your oxalic acid solution. And we're going to use a pipette to do this because it, again, gives us a lot of significant figures because volumetric pipettes are accurate to 2 decimal places. So we're going to add our acid to that flask. Then we're going to add our unknown base, but we're going to add this to a burette. So you should have cleaned and prepared this burette. You can clean it with some distilled water first, and then you add your unknown base to it a little bit to rinse it through, and then fill it all the way. And once you've removed the air bubble, then you record the initial volume on the burette. So let's talk about how you read a burette because it's a little bit confusing if you haven't used it before. So with burettes, we're always going to read down, so you don't have to do any subtraction in your head because burettes tell you how much liquid has been dispensed, not how much it contains. And whenever we're reading a burette, we're going to round volumes to the nearest 0.05 milliliters. So let's look at our first burette here. This is an initial reading. So the markings here are every 0.1 milliliters. So we've got 0.1, 0.2, 0.3, etc. And the marking here is 0.7, and then we're kind of between 0.7 and 0.8. So I would read this volume as 0.75 milliliters. On this next burette, we're between 49 and 50 milliliters. Again, each marking is 0.1. We're reading down, and so here we're between the 0.3 and the 0.4 milliliters, so we've got 49.35 milliliters. And the difference between them is how much liquid was dispensed. So what you're going to do is titrate with the base. You're going to dispense the base from the burette until the color of the solution is faint pink. Then, once it's faint pink, you're going to record the final volume of the burette. In your data sheet. So the difference between the final and the initial volume is how much of the sodium hydroxide you used to complete the titration, and you'll do 2 trials of this. So you'll dump out the first solution, follow all of these steps again to do 2 trials. So you should have similar volumes for both trials. So when we're thinking about the concentration of that unknown sodium hydroxide solution, we start by writing a balanced equation. We have oxalic acid, it's aqueous because it's dissolved in water. We are adding sodium hydroxide, and this is a double displacement reaction, acid-base, so the H goes with the OH, the sodium goes with the oxalate ion, and we know that C2O4 is a 2- ion because we have 2 H's with it on the left, so we need Na2, C2O4 on the right to make it neutral, and the other product is water, or HOH. So even though we have H2 on the left, we only need that subscriptive 2 because the oxalate ion is a 2- ion. We don't keep the 2 in the formula of water. We got H2O because it's HOH. Then we balance by putting a 2 in front of water and a 2 in front of NaOH. So this is the balanced equation we're going to come back to. Now we need to know the sodium hydroxide solution. So we're using 10 milliliters of acid, and this is our known solution. We calculated the concentration of this before. And we've got 15 milliliters of our unknown. The first step is going to be to take the volume of our known, converted to liters. So 10 to the minus 3 liters per milliliter, or 1,000 milliliters in a liter. We use the molarity that we calculated above, so moles of oxalic acid per liter of solution, and then we use the mole ratio. So we've got 2 moles of sodium hydroxide for every 1 mole of oxalic acid. This gives us 0.002260 moles of base, and the volume of base that we used is 15 milliliters, and we're going to convert this value to liters because molarity is always moles per liter. We get 0.1507 molar of our base solution. Your value may not be exactly the same as this one. This is just an example. Then you repeat this calculation for your second trial. Then what we're going to do is dilute the oxalic acid and do another set of titrations. So what we're going to do is dispense about 15 milliliters of oxalic acid into a volumetric flask. So the way you do this is you're going to just pour the stock acid, some of it, just about 15 milliliters, into a graduated cylinder. And then take that and put it into a clean volumetric flask. Once you have your stock acid in a clean volumetric flask, we're only going to use part of it. Then we're going to fill the volumetric flask halfway with water, swirl to mix. Then we're going to repeat what we did in part A, fill the flask to just below the line with DI water. Use a dropper to get to the line, then stopper, hold, and invert to mix. So now that we have that diluted solution prepared, now we need to know its concentration. So we're going to use C1V1 equals C2V2. This is the dilution equation. Our stock concentration that we found in part A is 0.113 molar. The volume is about 15 milliliters. We don't know that to as many significant figures, but that's okay. And then we know that the final volume is going to be 100 milliliters. Then we calculate C2, and in this case we get 0.0170 molar of our oxalic acid. Then we titrate, so we're going to add water and indicator to our Erlenmeyer flask, plus we're going to add our oxalic acid. and this is going to be the diluted solution. We will add some more of the unknown base to the burette and record the initial volume. Titrate with the base. Record the final volume. And we repeat the titration, then you clean up and calculate the concentration again. So if we used a 10 milliliter pipette to measure out our acid and we titrated with only 2.25 milliliters of unknown base, let's think about what's happening. The balanced equation is the same, so even though we diluted the acid, we didn't change its identity. So the balanced equation is still going to be the same as we had in part B. We will start with the volume in liters of our known solution, but the concentration that we're starting with is different because now it is diluted. So this is the diluted concentration. We will still use the mole ratio from the balanced equation. Now the moles will be fewer, but we also used a much smaller volume, so that makes sense. Again, whenever you're calculating a molarity, that needs to be in moles per liter, and we get 0.151 molar NaOH. Essentially, we got the same concentration, but the volumes were different. And that's what you should expect, the same concentration of NaOH, regardless of whether you use the concentrated or the dilute acid, because we never change the sodium hydroxide by diluting it or making it more concentrated. And that is experiment 5.